My dear students, so we were discussing about unevenness of the textile strand. So we have discussed about the definition of unevenness or irregularity in textile materials, the types of irregularities such as short term, medium term and the long term irregularities, the index of irregularity, limit irregularity, the causes and effects of irregularity in the textile strand. After that, we have discussed about the various measurement methods of irregularity in textile materials such as yarn, robin, and sliver. So, among those measurement methods, one of the instrument which is most popular, that is the Worcester evenness tester. So, we have discussed about the principle of working of Worcester evenness tester, which is the capacitive method. Now we shall proceed further. We will now discuss about associated Worcester equipments. In the associated Worcester equipment, there is one imperfection indicator. Imperfections are a specific type of irregularities in the textile yarn. Particularly in case of staple fiber yarn, the definition of imperfection is like that: at a number of places along the length of the staple fiber yarn, there are some large variations in mass per unit length which are referred to as imperfections. They are thick place, thin place and naps in the yarn body. So now definition of thick places. Thick places are more than 50% enlarged diameter than the average diameter of the yarn. So if there is the thickness of the yarn which is more than 50% of the yarn diameter, then that particular place is called thick place. So the diameter will be 50% higher and the length of that thicker region should be more than 4 millimeter and maximum up to the staple length of the fiber. So in case of Worcester tester, that thick place knob is set to at position 3, and there are various ranges of thick places such as more than 100%, more than 70%, more than 50% and more than 35% enlargement in the thickness of the yarn diameter, thickness or the yarn diameter, also called as thickness. Now next is thin places, that is the less than 50% of the mean yarn diameter, that is called thin place. So thin place knob is set at less than 50% value, and various ranges of thin places are less than 60% or minus 60%, minus 50%, minus 40% and minus 30% of the average value of the mean yarn diameter or mean mass of the yarn. Now next is the naps. A fault length of 1 millimeter only, but the cross section dimension is more than 200% of the average value. Okay, so more than 200% means more than double. If naps is there, that means the dimension of that particular fault is 1 millimeter in the length of the yarn, and the diameter at that position, that is more than double of the normal yarn diameter. So that is called naps. So there are naps of various ranges such as more than 400% of the yarn diameter, more than 280% of the yarn diameter, or more than 200% yarn diameter, or more than 140% of yarn diameter. So there are the various ranges of setting can be done in the Worcester equipment for the detection of the naps. So these thick places, thin places and naps are called yarn imperfections. Now another parameter which is obtained by the evenness tester, that is called spectrogram. So spectrogram is basically one kind of histogram. You know, in the statistics, the histogram or frequency distribution So here the histogram between the cut length of the yarn versus amplitude of the yarn irregularity or mass irregularity has been plotted. So amplitude, that is the diameter of the yarn. Okay, if there will be the enhancement of the diameter such as thin thick places or naps, so that will be the amplitude. And when we are going to plot the cut length versus amplitude in the histogram, then very basically we will try to understand the periodic variation. That means the variation which is repeating once again and again after certain interval. So if there will be certain kind of periodic variation, so that means one same fault is occurring after a certain interval of length, then that is called periodic variation. So that kind of periodic variation if exist in the yarn body, so then you will see there will be a certain enlargement of a particular class value or amplitude, like a chimney shape. So you will see in the histogram there is a smooth curve like normal distribution, but when there will be periodic variation, then there will be a certain enlargement of the amplitude, that is like a chimney in a particular factory. So this kind of fault or this kind of appearance is called chimney type spectrogram. So if there is a chimney type spectrogram, then one can be assured that there is certain serious periodic fault exists in the material. So histogram will give us the information on that. Now, what are the outputs of a star evenness tester? The data relating to the test material, machines and test house particulars, that is the first information one can obtain from the star evenness tester. The test material, the detail about the test material, that means if it is a yarn, if it is a sliver or if it is a robin, that will be detailed, will be given. Then the machine, in which machine the evenness test was done, what is the model name and the specifications of the machine, that will be also obtained. Then test out particular, that means the relative humidity and temperature uh, of the testing house or the laboratory, that will be also provided by the star evenness tester. Then the U percentage, CV percentage and imperfections values of the yarn, that will also be obtained. You know what is U percentage, what is CV percentage and what are the imperfections, already I have discussed. Then the spectrogram already I have discussed in the last slide. The spectrogram also will be obtained by the evenness tester. And the fourth information which will be obtained, that is the variance length curves. So variance length curves, that is the variance between the length and variance within the length, that graph will be obtained, that already I have discussed in my previous lecture. So these are the four common information that will be obtained by one star evenness tester. So now you need to know how to predict those graph, how to predict the U percentage, CV percentage, how to predict the spectrogram if it is a chimney type spectrogram or if it is a hump type, or if it is a hill type spectrogram, that I shall discuss later, that also you need to interpret. Then the variance length curve, how the variance length curve are actually obtained, if the curve is smooth one or there is a variation ups and downs in the variance length curve, that also we need to interpret. Now spectrogram showing periodic fault of chimney type. So here you can see there are two spectrogram. The first one, the top one, is a chimney type spectrogram where a certain increment of the amplitude is shown here. That is a chimney type spectrogram. So this spectrogram will give you information about certain serious periodic fault in the material. So a chimney type spectrogram consisting of one or more peak is normally due. The mechanical faults such as eccentric roller or gear, if the gear or the roller is eccentric, in improper meshing of the gear and missing of the teeth in the gear, if some teeth of the gear is broken or the wheel, then this kind of chimney type spectrogram will be obtained. So if there is a chimney type spectrogram obtained, then there may be any kind of such fault, that is that due to this reason this kind of faults are obtained in the material. Then another type of spectrogram, which is the bottom one. Here we will see the chimney is not there, but still there is a bump is obtained. There's a hill is obtained. It's called hill type spectrogram. Hill, okay, hill type spectrogram or bump type spectrogram. If there is a hill type spectrogram obtained, that is due to the drafting wave. The spectrogram showing periodic fault of hill type. A hill type spectrogram consisting of one or more peak is normally due to the drafting waves caused by the factors such as improper setting in the drafting zone, improper pressure applied by the top rolls, too many short fibers in the material. They are the reason of the irregularity, mass irregularity in the textile material, and due to that, that hill type spectrogram will be obtained as a periodic fault. So spectrogram is a very strong tool to understand, to analyze the periodic faults in the textile material. Either it is a hill type or it is a chimney type of spectrogram. Then come to the variance length curve. So you will see here in this figure, this is a variance length curve, CV percentage versus length of the specimen. So there are two graphs. One is A, which is a straight line, smooth graph, straight line, and this B. B is little curvy graph. Okay, ups and downs are there. It is not a straight line. There are two type of specimen are giving two type of variance length curve. So A is the straight line, so the fault-free yarn tested curve. So A is a fault-free yarn. If the yarn is having no fault, no defect, then you will see such kind of smooth straight line curve. And if there are some fault in the yarn, thick place, thin places, irregularity, imperfection, then you will see irregular variance length curve, which is like a B. Okay, so in this way we can interpret what is the variability, type of variability, and amount of variability present in the textile material. Then come to another parameter which is called diagram. So diagram is different from the spectrogram. Diagram is a graphical representation of mass per unit length variation along the length of the sliver rubbing of yarn is referred to as diagram. So it's a mass per unit length variation. It's not amplitude. In the spectrogram, it was amplitude versus the length of the specimen. In the diagram, it is the mass per unit length variation versus the length of the specimen. It indicates the nature of the variability present in the material. So what is the nature of variability that will be obtained in the diagram? We will obtain the following information from the diagram. Long wavelength variation. Okay, if it is a long term variation, even with the periodic variation when spectrogram cannot confirm. If it is a long term variation, already I have defined long term variation, which is having a long wavelength, that will be detected by the diagram. That is not obtained in case of spectrogram. The spectrogram will measure the short and medium term variations, periodic variations, but the diagram will measure, can be able to measure the long term variation. Now extreme thick and thick places. If there are extreme thick and thin places, that means thick places and thin places are detected in a very long distance. That also can be obtained by diagram. That is not detected by, sometimes not by the spectrogram. Slow changes and step changes in the mean value. Okay, if there are slow and step changes of the mean value, suppose for example the mean yarn count is 40 count, okay, and gradually the same count is running in a ring frame machine for 1 month. So maybe after 1 month there is a slow change of the mean value from 40 count to 36 count. So that slow changes for after 30 days, that can be detected by the diagram. That is not detected by spectrogram, because the spectrogram can only obtain, can only detect the short term variation. The long term variation can only be detected by the diagram. In many cases it can confirm the numerical value of the instrument. So numerical value of the instrument also can be confirmed by the diagram. That is also possible. Now the next method, that is the photoelectric method. So whatever method I have discussed now for the Worcester evenness tester, that is working in capacitive principle. Now this instrument that will work in the photoelectric principle. Photoelectric, the name itself implies that when the photo or the light will be incidented on a photoelectric cell, it will generate electricity, okay, like a solar cell. So when the beam of light is directed into photoelectric cell, an electric current is produced. Okay, so when the beam is light is incidented over a detector, then the electric current will be produced. Now, if the textile yarn is actually present on the path or on the way of the incidented beam of the light, then the yarn will be working as an obstacle for the propagation of the light beam. And the light beam will not be able to reach to the detector, and as a result, the electric signal will be reduced. So, the amount of electric signal will be measured, and the instrument will give you the information about the diameter of the yarn based on the electrical current generated by the detector or the or the photoelectric cell. The yarn diameter will be measured. It's a indirect principle. So this is the diagram of the instrument is shown here. It's a light source. Okay, it's a lens which will convert the divergent beam of light to a parallel one, and there is a slit. In between the slit, the yarn is moving. Okay, when the yarn will be there present on the wave of the beam of light, then the beam of the light will be restricted, so only the few light rays outside the yarn diameter, they will come to the photoelectric cell, and as a result there will be the current generated. The electric current will be measured by an indicator. So now indicator is calibrated in terms of the diameter of the yarn, and that will be plotted in some graph, the zigzag graph that is showing, that is depending upon the variation in the diameter of the yarn, there will be the graph will be produced. If there is no variation of the diameter of the yarn is perfectly regular. So in that case, this graph will be perfectly straight line. But as soon as there will be the variation in the diameter of the yarn, there will be the variation in the electricity produced by this instrument, and as a result, there will be the variation in the graph or fluctuation in the graph will be obtained. So that will give you the impression about the irregularity in the textile material. This is a photoelectric method. Now, this effect, the advantages of this instrument is that this is unaffected by moisture. So, if the yarn is a hygroscopic material, it can absorb moisture. So, the presence of moisture will not affect the amount of electricity generated by the instrument. But in case of capacitive principle, which is they are used in the Worcester, so in that case, when the moisture will be present in the yarn, then dielectric property of the yarn will be changed. As a result, the capacitive value or the capacitance of the capacitor will change, and the result also will change. So Worcester evenness tester will work on a predetermined moisture regain of the material only. If the moisture regain of the material will be changed, then the result of the Worcester also will change. So it's a drawback of the Worcester evenness tester, which is working in capacitive principle. But here in this photoelectric method is more accurate than that of the Worcester. Then optical method, another method, optical method, where the infrared radiation IR method, infrared radiation is used for measurement of the irregularity of the yarn. So the name of the instrument is Jewel G580. So in this optical method, actually the infrared radiation is actually used for measurement of yarn diameter. So yarn is passes at a speed through one of the beam, blocking a portion of the light, measuring the receiver. So here you can see the infrared radiation. This is the source of the infrared radiation, and from the source there are two identical beam of infrared radiation are generated. One beam of light is incidenting on receiver I2, and another similar beam is incidented over the reference receiver I1. So there are two receivers I1 and I2. So in front of the I2 receiver, the yarn is actually placed, or yarn is actually passed through. So as a result, yarn will block some of the infrared radiation. So that infrared radiation will not be able to come to receiver I2. Now this both receiver I1 and I2, they are identical, and they will connected with some computer system for measurement of the intensity of the infrared radiation. Now, initially, when there will be no fiber or the ion present, then the intensity of both the receiver I1 and I2 will be equal. There is no difference between the intensity of the infrared radiation detected by I1 by and I2. But as soon as there is the presence of the ion as per the diameter of the ion will block some part of the infrared light. As a result, there will be the deviations, or there will be the difference between the intensity of the light detected by I1 and I2, and that difference will give you the measurement of the ion diameter. So now the computer system will produce some graphical representation. If there will be no variation in the ion diameter, then this line, the graph line, will be a constant line, a straight line. But as soon as there will be the variation in the ion diameter, there will be some zigzag curve will be produced based on the variation in the diameter of the yarn. So as a textile yarn never be very smooth, and diameter never will be constant. So there will be always some variation in the yarn diameter, and as a result there will be some uh, vibrations or fluctuations in the curve generated by the system. So this will be the measurement of the unevenness of the yarn. So optical method is claimed to be nearer to the human eye in the way it sees fold. As it's like optical methods, as we see our eye, human eye, is also working under optical principle. So as we see the variability on the yarn, how it is thicker, thinner, or uneven in nature, the similar way this optical method also will detect and measure the unevenness. So it is more resembling how the humans are watching over the textile specimen regarding its unevenness. So that's why this with this concept, this optical method of measurement of yarn unevenness was invented by the Jugel G580. The optical method measurement measures the variation in the diameter of the yarn and not in its mass. So it's a basically measurement of the diameter of the yarn. It is not the measurement of the mass, because it is blocking the infrared radiation, and the blockage of the infrared radiation is done by the diameter of the, or the cross-sectional shape of the yarn, not by the mass of the yarn. So it's not a mass irregularity, it is basically irregularity in diameter or the cross-sectional shape of the yarn. For a constant level of twist in the yarn, the mass of a given length is related to the diameter by the equation mass equal to CD square. Okay, it's relationship between the mass and C and D. C is the constant and D the diameter of the yarn. So C is a constant, so mass is directly proportional to diameter square of the yarn. So if one can measure the unevenness or variation due to the diameter, so from this formula one can be able to calculate the mass variation of the yarn. So this kind of formula can be used for prediction of mass variation of the yarn from the diameter variation of the yarn. This method is not affected by moisture content or fiber blend variation in the yarn. So sometimes when you are using the blended fiber, such as polyester cotton blended fiber, so in that case if you will go for the measurement in Wooster tester, so due to the presence of two different type of fiber, their dielectric properties are different. The dielectric constant of the cotton is different, and dielectric constant of the polyester is different. So their combined effect also will be different. If you are going to use different blend ratio, such as 80-20 blend ratio, or 60-40, or 70-30, so in every case, though you are using the same yarn count of same mass irregularity, still you will get the different value due to their differences in the dielectric constant. So this is also one kind of drawback with the, or limitation with the Wooster unevenness tester. So this kind of drawback can be avoided when you are going to use this kind of IR method for the measurement of the yarn unevenness. So IR methods and photoelectric method, they are unaffected by moisture and they are unaffected by fiber blend variation. So in this way, these methods are superior than that of the Wooster unevenness tester. So that's all. This is the end of this unevenness measurement method and end of the syllabus for this semester. I hope you have enjoyed the lecture. Best wishes for your end semester examination.